Are you ready to do a definite integral review? So our purpose here is not so much to define the integral or to prove anything about the integral, but rather to review basic properties that will help one when one is using it in areas like probability. Let's start. So suppose that A is less than B, these are just two numbers. Then the backbone of computation is the fundamental theorem of calculus part 2. And it says that if little f and capital F are continuous functions on the closed interval a, b, and f satisfies that the derivative of capital F is equal to little f on the open interval a, b, i.e. capital F is an antiderivative, then we have the following net change formula, that capital F at b minus capital F of a is equal to the integral from a to b of little f, the Riemann integral, the definite integral. And so we know from the definition of this Riemann integral that that is the area below f, where f is positive, minus the area above f, where f is negative. And so according to this picture, that would be a1 plus a3 minus a2 minus a4 in this case. Notice here that little f drawn above was drawn as a continuous function. Now the fundamental theorem of calculus part 2 allows us to transfer properties known for the derivative to these definite integrals. So in particular, the integral from a to b of f inherits the following properties. Linearity, the integral from a to b of alpha f plus beta g is equal to alpha times the integral from a to b of f plus beta times the integral of a to b of g. Said simply, the integral of a linear combination is equal to the linear combination of integrals. So here alpha and beta are just fixed real numbers. It also inherits the adjacent interval property. So if you wanted to integrate from a all the way up to b of f, you can integrate from a to c of f. Then you could pause, get a snack, have a beer, come back, and then you could integrate from c to b of f. Domination. If we have two functions that we want to integrate, and one of them, f, is always less than or equal to g on the closed interval of interest, then the definite integral of f is less than or equal to the definite integral of g. Direction. If we wanted to integrate from b to a of f, then this is equal to the negative of the integral with the right way around from a to b of f. Evenness. So if we had the property that f of minus x is equal to f of x, and we wanted to integrate from minus a to a of f, well then that's just simply 2 times the integral from 0 to a of f. Both parts from minus a to 0 and the part from 0 to a have to be the same because of the evenness. Oddness. If we had the property that f of minus x is equal to minus f of x, then the integral around 0 again, so from minus a to a of f, has to be 0. Let's take a simple example. So suppose we wanted to integrate from minus 1 to 1 of 3 times sine x plus 4 times the absolute value of x. This is a linear combination. So we could say alpha is equal to 3 and beta is equal to 4. And we could use the fact that the integral of a linear combination is equal to the linear combination of integrals to express that as 3 times the integral from minus 1 of sine x plus 4 times the integral from minus 1 to 1 of the absolute value of x. Now we know that sine x is an odd function. It satisfies, or sine of minus x is equal to minus sine of x. And so by the oddness above, this first integral is 0. So we're going to have 3 times 0. On the other hand, the absolute value of x is clearly even. If you plug minus x into the absolute value, you get the same number as plugging x in. And so this other integral, 4 times minus 1 to 1 of the absolute value of x, well, that has to be equal to 4 times another 2 times the integral from 0 to 1 of x dx by the evenness property above. And so we have 4 times 2, or 8, times the integral from 0 to 1 of x dx. And now we're going to use a fundamental theorem of calculus. Little f is just equal to x here, so little f of x is equal to x. But we also know that the derivative of x squared over 2 is equal to x. Our antiderivative, capital F, is equal to x squared over 2. And so this initial integral is just reduced to 8 times x squared over 2 evaluated at 1 and then negatively at 0 by the fundamental theorem of calculus 2. Quickly substitute 1 in and you're going to find out that the answer is 4. Let's look at another example. So the integral from 0 to infinity of t times e to the minus t squared over 2 dt. Little alarm bells should go off and you should realize, well, this is really an improper integral. Improper integrals are defined as limits. So this is really the limit as m goes to infinity of the integral from 0 up to m of t times e to the minus t squared over 2 dt. But now we evaluate this integral inside the limit in the same way, using the fundamental theorem of calculus. Just a is 0 and b is m. We look for an antiderivative, and to do that, let's try differentiating minus e to the minus t squared over 2. And we just use the exponential rule, which says the derivative of the exponential of a function is equal to the derivative of the function times the exponential of that same function. In this case, it gives us negative e to the minus t squared over 2 times the derivative of minus t squared over 2. And this very simply is equal to t times e to the minus t squared over 2, since the negatives will cancel out and the derivative of minus t squared over 2 is just equal to minus t. So f of t is equal to minus e to the minus t squared over 2 is an antiderivative. And we can just evaluate the integral from 0 to infinity t times e to the minus t squared over 2 as the limit, m goes to infinity, of the integral from 0 to m. And then we can substitute in our net change using the antiderivative to find out that the integral from 0 to m is equal to minus e to the minus m squared over 2 minus e to the 0 squared over 2, which of course is just 0, and then let m go to infinity. So this first term, minus e to the minus m squared over 2, goes to 0. And the second term, which is minus e to the 0 is 1. The minuses cancel out, and we're just left with 1. So what we learned is definite integrals can be evaluated using antiderivatives and net change. And this formula is really what is known as the fundamental theorem of calculus part 2. This also, in addition to facilitating calculations, gives us properties of the definite integral, like linearity. The integral of a linear combination is a linear combination of the integrals, like direction change, like evenness and oddness. We also discovered that even improper integrals can be solved using this net change and the fundamental theorem of calculus and these properties. We just have to remember that when we're evaluating an improper integral, that it's really a limit. And so when we evaluate the antiderivative at the upper, the lower, or both limits, it is actually a limiting process. Thank you.